Hey guys, this is Omar, and today I'm going to walk through the ANOVA Lab from Module 3, Section 21. It's the last lab in that section. So let's just dive right into it. It seems like it'll probably be pretty easy because the README doesn't cover a lot of material. It really just tells us how to pull the ANOVA table using an OLS object. So let's get into it. Start by loading the data in the stored file. Okay, I already did that. Let's do that again. Generate the ANOVA table. Okay, well, it would be nice if I could get a code cell, but that's okay. I have one here. So I have my outline. I'm literally just going to copy and paste it. I'm sorry. Actually, that is not my outline. That is my outline. Okay. Okay. That's the ANOVA code. Let's just select it, copy it, paste it in, and then the formula is going to be, okay. Well, let's inspect the table, display TF. Okay. And it says, okay, use ANOVA, load tooth growth, okay. And it says what we want to do is generate an ANOVA to analyze the influence of the medication and the dosage. So that's the dosage, that's which medication it uses, and that's the tooth growth. So I'm guessing that length is the target variable, and this is a categorical, and dosage is not. So we're going to modify this by saying len, sup, and dose. Len is the target, so let's go down here. Hang on, I'm just going to, okay. Len, sup, and dose. Okay. So let's make it len, sup, because, yeah, that's the categorical. And then dose. Let's delete that, and let's see what that does. Ha! Okay, that went through. Okay. Degrees of freedom, the probability. Okay. There was code here. Oh, my bad. Okay. Interpret the output. Make a brief comment regarding the statistics and the effect of the supplement and dosage on the tooth length. Okay, I want to say that the supplement that we use made a big difference compared, sorry. It's the opposite, actually, because it's a small p-value, I think. So that means that dosage had much greater impact on the target variable than the type of supplement used, although that also was significant because it seems it's e to the -3, so it's a small value, which I think means something. Okay, compare to t-tests. Now that you've had a chance to generate an ANOVA, it's interesting to compare the results to those from the t-tests you were working with earlier. With that, start by breaking the data into two samples, those given the OJ supplement and those given the VC supplement. Afterward, you'll conduct a t-test to compare the tooth length of these samples. So let's have two data frames. So let's have the OJDF, which is equal to DF, where sup, right? That's the name. Sup is equal to OJ. Okay. DF, where sup is equal to OJ. And then we have VC DF, which is equal to df where sup is equal to vc. Okay, so we're going to break that up. And, oh, what did I do? Key error false. What do you mean key error false? Did I do something wrong here? Oh, I'm sorry. df where df is equal to. Where df sup is equal to. My apologies. That, I think, was just cycling through the key, the index, and trying to find sup, which did not exist. That worked. Okay. Actually, for good measure, let's display ojdf.head and something. So let's make it VC. Okay. Yeah, that's all OJ. That's all VC. So that seems like it probably worked. Alrighty. Now run a t-test between these two groups and print the associated two-sided p-value. Oh man, I forgot how to do that. Well, let's see. Did we import stats and stuff? Statsmodels.api as SM. Okay. Just gonna hang on. Okay. And we want to do, this is probably going to be a two-sample unpaired, two different unrelated samples. Okay. Right, because we're comparing this treatment versus that treatment. So that's going to be this one. Alrighty. How do you even do the two-sided? I don't even know. This is a two-sided test for the null hypothesis that two independent samples have identical. Okay, so that should be simple enough. Let me just make sure that I have imported the appropriate. Okay. That should not be a code block. That should, okay, hang on. Okay. Well, import scipy.stats as stats. Result is equal to this. Actually, well, let's do it length, right? Okay, so we're going to do, hang on. Okay. And then let's re-slice it up here, or can we do that? Okay. Len. Oh, yeah, that worked. Okay, so that'll do it. So let's just do OJDF versus VCDF print result. Okay, so the statistic is 1.9, the p-value is 0.06. That's like right on the threshold. Okay. Now recalculate an ANOVA F test with only the supplement variable. So take out the dose variable. Okay. An ANOVA F test between the two categories is the same as performing a two-tailed t-test. So the p-value should be identical to your calculation above. Maybe a small due to a rounding error. Okay, let's try that. Oh. What did we do up here? Yeah, let's just copy that part. Okay. So I think we can just modify the formula. So we're just going to take out dose and then see what that does, right? Oh no. Okay. Oh, yeah, oh, they were right. The p-value is virtually the same. 0.060393, 0.060393. Yeah, so they were right. Okay, well, good to know. Run multiple t-tests. While the two-category ANOVA test is identical to the two-tailed t-test, performing multiple t-tests leads to multiple comparisons problem. Okay, to investigate this, look at the various sample groups you could create from the two features. I see what they're trying to say. For group in df.group by, okay, length. Okay, so we're going to group them by sup and dose and then just pull length, right? And then group name is equal to group 0. Okay, data is equal to group 1. Print group name. That's what we get. Okay, well, bad in practice. The effects, examine the effects of calculating multiple t-tests with various combinations of these. To do this, generate all combinations of the above groups. For each pairwise combination, calculate the p-value of a two-sided t-test. Print the group combinations and their associated p-value for the two-sided test. So they're saying pairwise combinations meaning what exactly? I'm not sure what they want here exactly. Generate all combinations of the above groups. Oh, so OJ 0.5 and OJ. Okay, that's a lot of combinations. I don't even know how you go about doing that. Okay, so let's make the combinations with iter tools, and we're going to do combinations of all groups and of 2. And then I just want to print comms and see if that does what it does. Oh, list. Okay, good. So that gave me all the combinations. Each one of them is a tuple. 0.2, 0.5, VCO5. Okay, that's a good thing. So now we can just loop through each combination. And what are we going to do? Okay. Do a t-test on each one. I think I might need to do an enumerate here. Hang on. Wait. Pause. So I took a look at the solution, and it seems like they're basically doing pretty much what I'm doing. They just sort of declare sup1 and dose1 as variables, but they're slicing out the combinations in the same way. They also use a list comprehension to come up with groups where I don't think that I do that. Yeah, the result is essentially the same. And then they slice sample 1 to df, they get the length. Kind of same. I split that up into 2 pieces. Because I didn't realize that I tried to use and as an A and D, but I forgot that that's the operator you have to use if you want to have, like, what is it, conjunctive conditions or whatever, inside of a df slicing thing. But the result is the same. Yeah, and then they get the probability, and then they just print combo and then P for each one. I popped them in a list and did that, and this is just the back. Let's just take a second. The way that I would do it is I would print com and result 1. That does it. There you go. Yeah, and then my results are like similar, slightly different because I guess, I don't know, maybe the seed is different or something. I don't know, but kind of the same. Yeah. Somewhat similar values that we're seeing here. All right, so hope that was helpful.